To look at your inequality first and make a reference to what types of numbers you're looking for. Okay, so if it says greater than 0, you're looking for, that's another way of saying what type of numbers? Positive. Okay, so when we're working inside our sign chart, that's what we're looking for. We're looking for the positives. Okay, so it might be a good idea just to jot that down so you know what you're doing. We also have a greater than sign, so there's no equality here, right? No equality, so you're using all parentheses when we write our intervals. Okay. What this one has done is it's pretty nice, is that it's already factored for us, right? You may see from time to time this being multiplied out. Okay. And you have to go through your hierarchy of factoring, GCF, A times C method, factored by grouping, quadratic formula. None of that stuff works. You're going to then use the rational root theorem. And hopefully if you get to that point, maybe you use your technology to get you a good start on that. But what we do is we take, once it's in completely factored form, and you've isolated 0 on this side, you're going to take the zeros and put those on a number line. So, create a number line. We got a 0 of 1. So we'll put that in there. We got a 0 of -2. We have a 0 of +3. And we have a 0 of -4. Once you identify those zeros on your number line, I just think it's a good organization thing to draw those straight lines down. It just helps you keep things aligned correctly inside your intervals. I have seen people, even put those lines horizontally with their factors that they write over here on the left-hand side. I don't think that's extremely necessary. I think most of you probably have line paper anyways, so you can keep track of it that way. But then you're going to write down your factors: x minus 1, x plus 2, x minus 3, and x plus 4. And then the last one, if you can't forget, is your total polynomial. Okay, and I just write total down there. It's a little bit easier to write this whole thing out. But what we're looking at, just kind of rehashing what we talked about yesterday. When you know what x is, let's say if x is 10, you would know this would be a positive number there, right? You would know that this is a positive number. You would know that this is a positive number, and that's a positive number. So when you multiply positive numbers together, all 4 of them are positive, what's your result going to be? Positive, which is a number greater than 0, so you're good there. But if, like, say, x was 0, here you would have a negative, here you would have a positive, here you would have a negative, and here you would have a positive number, right? So I'm multiplying a negative times a positive times a negative times a positive, and I don't care how big the number is. For instance, if I did choose 0, we'd have what? -1 times 2 is -2 times -3 would be 6 times 4 would be 24, right? It'd be positive 24, but I don't care. I just want that it's positive. It's above the x-axis, right? So what we're going to try to do is we're going to try to take values like that and say, okay, well, what if x was 7? What if x is 4? What if x is 6? What if it's 2.8? Okay? And start seeing where all these positive and negative numbers occur when we multiply them all together. However, this system here is going to create intervals in which force you or provide you choices that make sense. Because if we think about graphically looking at this, remember these are zeros, right? So if I'm looking at my graph, a 0 is where we either cross the x-axis or we bump it and go back down or go back up from where we came from, right? So those are really the only possible places that a sign could change, on the left-hand side or the right-hand side of a 0. So that's why we put those on. That's what they, or why they break up our interval here, our intervals. So we're going to test those in this chart. Provides all the different types of combinations you could have with pluses and minuses up in this 4-factor polynomial. Okay, so let's just choose a number that's over here. It doesn't matter. I like to, when I choose numbers to the left and to the right of my last zero or my first zero, I like to choose things that are pretty big. It makes the algebra a little bit easier. So if I go like -10, well, -10 minus 1 is still a negative. -10 plus 2 is still negative. -10 minus 3 is still negative. -10 plus 4 is still negative. All right. Subtracting or adding something to a very large negative number keeps it a negative number. All right. So now, ultimately, what we're doing is we're looking for an odd number of negatives, right? An odd number of negative signs will always produce a product that is negative. Here we have an even number, right? So if we have an even number of negatives, our product should be positive. Okay. As we go through in this middle region, you got a lot of numbers in there, but what's the best number to use inside this interval here between -4 and -2? -3. Okay. When you can use integers. So -3 minus 1, negative. -3 plus 2, a negative. -3 minus 3, a negative. And -3 plus 4, a positive, right? That's then going to give you a negative there. We're going to go over here. What's a good number between -2 and 1? 0. So 0 minus 1 is negative. 0 plus 2 is positive. 0 minus 3, negative. 0 plus 4, positive. So now what's my total then? Positive. And I would try maybe 2 here. 2 minus 1. 2 plus 2, 2 minus 3, and then 2 plus 6, or sorry, 2 plus 4 is 6. And that's going to give me a negative total. And now choose really big numbers. If I choose like 50, subtract 1, add 2, minus 3, plus 4 to that, what kind of number do you always get? Positive. These are positive, and then my total is also positive. Okay. Now, as you're doing those things, you might be a person that can kind of visualize those things. If if I know that plugging in 50 as my x value is going to produce all those positive numbers, and you don't want to write all 4 of those plus signs down. You just want to go straight to the total and write your plus sign down. You can do that. I don't have an issue with that. Okay. The design of these charts are intended to provide you and organize all your information that you need. But if you feel that you can maybe produce some of that information without the complete chart and still be accurate, that's fine. So now, like we said, this is the reason I wrote up here positive. We're looking for positive numbers so that when I'm done, I always come down and I circle my positive values. Those are the ones that tell me my solutions that I'm looking for. And then I go back up to my number line and I just highlight those regions. Okay, because this is a number line from -infinity to positive infinity, right? And we just got a couple numbers that are highlighted off that. But we should also now shade in there. Now, can I use -4? No, because we just had greater than, right? So we put an open dot at -4. We skip over this stuff in the middle here because from -4 to -2 because that was a negative result. That was below the x-axis. So then should be another open dot at -2. I will shade up to 1. And then I'll skip over from 1 to 3. I get the 3 open dot there. And I'll continue to shade then to the right. And if they ever ask me a graphical representation of my solutions, that's it. That's fine. That's all you got to do. Okay. But I do think it's probably on WebAssign most of the time, they're going to ask you to write this in interval notation. Okay. So left to right again. What's the first number you see over here working left to right? -infinity. And then you get to -4. You're going to jump then to -2, right? So we get -2, and that's going to take me up to 1. And then we jump to 3, and takes me to infinity, right? And what do I do with those 3 intervals in? Union them. And those are all the solutions for that particular function. If we were to graph this, and I am going to type this into GeoGebra in a moment, but you will see that in those intervals, your graph is above the x-axis. Okay. All right, so I'm looking at x minus 1, x plus 2, x minus 3, and then x plus 4. Graph that thing. I'm going to ask you to find the zeros of that. I think I got to put my axes in. And we see here that from negative infinity to -4, negative infinity to -4. So if I look everything to the left of that 0, are you always above the x-axis? These y values are above the x-axis. From -2 to 1, from -2 to 1, are you back above the x-axis? Yeah. And then from 3 to infinity, are you back above the x-axis? Yeah. I don't know if GeoGebra will do this. Let's see here real quick. Yeah. It's kind of nice that it does that. You guys see what that means? They give you the number line, and it basically shows you exactly what we came up with. So I get these both on the same thing. Do these number lines tell you the exact same thing we came up with here? From negative infinity up to -4, and then from -2 to 1, and then from 3 to positive infinity. Not sure. I don't know if it's just a notation. Let me see here real quick. I'm not sure why it's positioned at a height of 1, but it is mimicking the results that we found. Is that doable? Okay. Let's do another one where we see maybe a different. I'm going to have it factored already for us again, but I see something a little bit different. So now you see some of your roots are going to have multiplicities, right? You've got a factor of 2x minus 6 to the 4th power. You got x plus 1 to the 3rd power. So we're going to kind of talk about what that means to us when we make our table. So this is what, a 8th degree polynomial. Okay. Obviously, if I were to give you something like this, it's going to be factored. Okay, I'm not going to make you factor an 8th degree polynomial. But you're going to still find your zeros. Okay, so and whether you want to write down its multiplicity, it's not, I don't think, a terrible idea. So when I find a 0, this one's going to give me, what, a 0 of 3. So maybe 3 is there. And it's a multiplicity of 4. I've got a -1. So maybe -1 is there. And it's a multiplicity of 3. And then obviously our last one is 2, right? So let me actually just give ourselves a little bit of room, put 2 in there. And it says less than or equal to, so less than or equal to, we're looking for what types of, yeah, we're looking for negatives. And we can include, right? We can include, because this equality portion, so we're going to use brackets if it's a value that's not infinity, right? And infinity always has to use the parentheses. So constructing then those lines there. Now you got 8 factors over here. My hopes are is that you don't write all 8 of these down. You could say 2x minus 6, 2x minus 6, 2x minus 6, 2x minus 6. But what are you going to know if I choose, say, 0? Is that going to be negative? 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 Does that make sense? Okay. So because these have a multiplicity of 4, you know that if I plug in some particular number and one of them is negative, all of them are negative. If one of them is positive, all of them are positive, right? So my thoughts to you are, you should know that if I have 2x minus 6, and I'm going to raise that to an even power. So I'm just going to write when I write my factors on the left-hand side and their multiplicities, I just write them as 2x minus 6 to the 4th like that, okay? You know that no matter what type of number you plug in, and you multiply it by itself 4 times, what are you going to get back? You're always going to get a positive number. Okay? So that's kind of a shortcut idea here to think that regardless of what we do here, we're going to get positives all across the board for that first one. All of those factors, right? Okay, all those signs for those factors. Now I do x plus 1 to the 3rd power. Now here's where you got to pay attention. Because a positive, let's say I choose 0 there. 4x, I get 1, right? Well, a positive 1 cubed is a positive number, right? But if I were to choose a number that provides me a negative there, isn't a negative 1 cubed still a negative? All right, so you get both, depending on the x values you choose, you have chances of getting positive and negative. So that one you can't do that trick with, right? And I don't know if it's a trick, but that logic that you're always going to get the same sign back. Okay? And with odd multiplicities, you may or may not. Okay, so the idea that this is cubed, that's an odd multiplicity, right? It's the same concept if I had x minus 2. Isn't x minus 2 an odd multiplicity? Just a multiplicity of 1, right? It's a trivial multiplicity, but it's still odd. So when you have odd multiplicities, you need to go through and actually find them. I would think that maybe you could probably, when you find that you have even multiplicities, are those plus signs really important? No, because we're just looking for odd negatives, right? That's what provides us negative results, negative products. So maybe even when you get even multiplicities, you don't even maybe have to pay attention to 2x minus 6 to the 4th. Okay? It's obviously never wrong to look at them and use them, but it is an idea, I would think. If I look at like negative 2, okay, because that's over here to the left of negative 1. If I plug negative 2 in here, what do you get? Negative 1, right? But then when you cube it, you get negative 1 again. Okay? And if I plug in negative 2 to this bottom one, don't I get a negative? Negative 2 minus 2 is negative 4, right? And I didn't write my total down here, but remember you need your P of X, or your total. And now I've got an odd number of negatives, right? So that would give me a total that is positive. And this is the idea that I was talking about, guys. If I have an even multiplicity here, does even having that one change anything? No, I know by default it's positive, and all I'm worried about is how many negatives I have. If I get into here, a nice number to choose would be 1, or sorry, 0, right? 0 plus 1 is 1, cube that is 1. 0 minus 2 is negative, right? Odd number of negatives gives you a product that is negative. Again, not having that first blue plus sign, does that really change my total? No. Come over here. Now, this is just kind of what stinks, is that I have to use a fraction, right? Okay, so 2.5. It's really not that hard. 2.5 plus 1 is a positive number. Positive number cubed is still a positive number. 2.5 minus 2 is still a positive number. Positive number cubed is still a positive number. So then we get a total that's positive, right? Okay. Now think about this. Just kind of think visually. Right now what we're saying is that whatever graph that we plot, the xy plane, when it comes to the 0 of 3, it is coming from above the x-axis, right? That makes sense? That's what those positive signs mean down at the bottom. Okay, between 2 and 3, we are above the x-axis. When I get down to 3, because I have an even multiplicity, what should happen at that 0 of 3? Yeah, it bounces off of it, right? It becomes tangent to that 0. So that should provide us insight that when we're done here, our total should be positive because of what we've already learned throughout the year about what happens at roots or zeros that have even multiplicity, right? So maybe having that understanding can provide you a little insight to help you make the recognition that when you are done, what you have done is correct or incorrect. Okay. So coming through here, if I choose like a number like 10, 10 plus 1 cubed is positive. 10 minus 2 is positive. 3 positives gives you a positive. And that idea right there tells us that at, if I was graphing this thing on the x and y axes, at 1, 2, 3 right there, on the left hand of 3, we're positive, so we're going down. We got to touch that 0, but then we bounce back up and stay positive. That's the concept that is happening graphically behind the scenes there. Okay. So we were looking for what type of solutions? Negative. Okay. So come down here to my negative. It's the only option that I have. Now can I include -1? Yes, because there is equality here. So we put in a closed dot on -1, closed dot on 2, and those are all the values that we're looking for. That interval, -1 to 2, is everything that we're interested in. Okay. What I like about these is that a lot of times they can like stagger the questions. They can say, okay, if I look at that polynomial and I ask you when it is less than or equal to 0, you can find between -1 and 2, inclusive. And then the next question might say, okay, same polynomial, but now where is it greater than 0? Well, everywhere else, right? It's the complement idea that we've talked about in the past. If I know where a polynomial is below the x-axis, we should automatically then know where the polynomial is above the x-axis. Okay? Again, if you wanted to graph that thing, you would see between -1 and 2. I just want to, I know you guys probably get tired of me going back and forth between these things, but I'm just interested in seeing what GeoGebra shows me when I do 2x minus 6 to the 4th x plus 1. I think there's a less than or I don't know if I've got to put like that there. That's less. A lot of times that's less than or equal to in like syntax for computer programs, or might be that one. Okay, you put those two signs back to back to one, or yeah, back to one another, and it'll do the less than or equal to. But I don't really care as long as I know what the less than is. I can put in the equal to stuff myself. If I look at that, is that -1 to 2? So that's pretty. I think that's pretty useful, maybe for you guys if you're trying to do this stuff on your own, or if you have your TIA 3 or your 4, you can type that into Y1, and you can see then that this curve looks something like that. Now you would make sure that your window is adjusted and everything. Now my Y values are going to get pretty steep here, so I'm not really probably going to pay attention too much to my Y values. Let's see if change the axes to a x-axis, y-axis. Let's go 1 to 50, see if that does anything. So we get down to 3,200, so that's quite a... Come on. Let's do that. So that's kind of what your graph would look like. Okay, messing up the scale of your y-axis though. But you see then that between -1 and 2, that's the only places that your graph is below the x-axis, right? Okay. Let's do a rational function. Okay. We talked about this. This is towards the end of the period yesterday, so we kind of got cut short. Whenever you have a rational function, and this actually is maintained for the polynomial functions too, or polynomial inequalities, you always want to get one side to be 0. So if they provide you maybe something that polynomial-wise, you don't have to write this. You can write that down, but when we get to what I'm going to write down right now, you don't have to. Just kind of pay attention. If I were to give you something like, I don't know, x times x minus 4 is less than or equal to -4, something like that. Okay. You still want to get one side equal to 0. And it doesn't matter which side, but I think it's probably easier to make the right-hand side 0 here. So you would do this: x times x minus 4 plus 4 is less than or equal to 0. Does that make sense? Okay. So you get everything equal to 0. But now you got to look at the left-hand side, and we should know that this is kind of foreshadowing. This is going to be something squared here, right? That expression. So go ahead, and what you need to do is you need to be able to put this thing into polynomial form. You need to expand that, so it gives me x squared minus 4x, and then plus 4 is less than or equal to 0, right? Then you can now factor that to what, x minus 2 less than or equal to 0. So now it's ready for the sign chart, right? So you might have to, with polynomials, go through that process where you move everything over. You might have to expand things to end up combining like terms and then factor in, right? Okay? It almost seems kind of counterintuitive to expand and then factor, but we have to do that first expansion so we can recognize that there are like terms that need to be added together, that kind of stuff. Similar concept when we talk about the rational function, and a lot, I would say that you see this situation occur a lot more with rational function than you do polynomial function. Because they want you to practice adding two ratios, subtracting two ratios, whatever. So we got x minus 3 over 2x plus 5 is less than or equal to 1. We're going to get one of these sides equal to 0, so I think it's probably easier to get the right-hand side to be 0. So we're going to write this as x minus 3 over 2x plus 5 minus 1 less than or equal to 0, right? Okay. Now, when I look at it that way, I can't do anything with this. I cannot work with this rational inequality when I have two ratios on the left-hand side. I need one ratio. Okay. So I need to add those two things together. What do I need to add ratios together? Common denominator. So when I find the common denominator, it's going to be 2x plus 5, right? So I'm going to multiply this thing by 2x plus 5 over 2x plus 5. So it's going to look like this. It's going to be x minus 3 over 2x plus 5 minus then, this thing becomes 2x plus 5 over 2x plus 5, right? That still says x minus 3 over 2x plus 5 minus 1. It's just a more convenient way of looking at that minus 1. Now, you can do the subtraction, right? And my common denominator of 2x plus 5 is less than or equal to 0. But now I do that subtraction. And this is just where you got to be very cautious. You're subtracting multiple things, right? So you need to subtract each part. You need to subtract the 2x, and you need to subtract the 5. Most people subtract the 2x, but then they add 5. Remember, I say quantity, and you need to subtract the whole thing. So you need to shoot that negative to both those parts. So I'm going to be left with x minus 3 minus 2x minus 5. And now you've got it in a format where you can combine like terms. X minus 2x gives me what? Negative x. Negative 3 minus 5 gives me negative 8. On the bottom I have 2x plus 5 less than or equal to 0. So now it's in a format where you can factor. Okay? What's nice is that's pretty much already factored, right? Go ahead and create your number line. You're going to put your zeros on there. Now, you put all zeros. Okay? Top zeros from the denominator or numerator and zeros from your denominator. Okay? So when I look at negative x minus 8 as a 0, is it going to be negative 8? Okay? So I'll put negative 8 in. And I look at the denominator, and I have negative 5 halves, right? So put negative 5 halves in. Maybe some of you prefer to look at it as negative 2.5. I think using, when you get zeros that are rational like that, with a fraction, there's nothing wrong changing to a decimal, because you're not going to choose that value. You're going to choose, if I see negative 2.5, I'm going to choose like 3, negative 3, or positive 2, or sorry, negative 2 to plug in, right? I'm not going to use that fraction. So if you want to write it as a decimal, that's okay. Nothing wrong with that. Then you're going to just plug in your zeros are here, negative x minus 8, and then 2x plus 5. So just like normal. Okay, just like we do with polynomials, you're going to write all your factors on the left-hand side. The one thing I kind of glazed over, we should probably pay attention to, is that factor came from the denominator, right? So the 0 that came from it cannot ever be used. Negative 2.5 can never be used. We have equality, right? So there's a potential that there could be a closed dot on negative 8 and a closed dot on negative 2.5, right? But because the negative 2.5 came from the denominator, I cannot use it. Okay? That's kind of the one intricacy that's a little bit different with rational polynomials, rational inequalities, than polynomial inequalities. Okay? You can't divide by zero, so you just got to make sure that you always put that open out there. Which would be if you're a person that is typing this in on WebAssign and you get it wrong compared to your neighbor that got it right, but you got everything the same. The reason you would have gotten wrong is you got a bracket and they would have had a parenthesis. Okay, so you can do all the work, that one symbol, basically making in the inclusion of that one value would throw everything off. So then we go through and we just pick up values in these regions again. So maybe I choose negative 10. Okay, just be careful here. When I plug in negative 10, I've got the opposite of negative 10 minus 8, right? The opposite of negative 10 is positive 10. Minus 8 is positive 2. Okay. And if I go negative 10 in that bottom factor, negative 10 plus 5 times 2 plus 5 is going to be a negative 1. Okay. So my total is then negative. Then we'll go between negative 8 and negative 2.5. So I don't know, maybe negative 5. Be a good value to choose. Negative 5 plugged in. So the opposite of negative 5 would give me positive 5. Minus 8 would give me negative 3. And if I try negative 5 here, in the 2x plus 5 factor, that's going to give me negative 5 back, right? Negative, negative, and my total then becomes positive. And now on the right-hand side of that last 0, what's a good number on that right-hand side to choose? 10 would be good. Better than that? 0. Okay? Wherever you can use 0, use it. So it's going to give me negative 8 for that first factor. And it's going to give me 5 for the second one, right? So my total is negative. Now, go back to your original problem. Okay? And I guess it doesn't really have to be your original problem. It could be, this one here. But what was the symbol we're looking for? Less than or equal to. So equal to tells me I can use brackets, right? But less than is looking for what type of numbers? Negative. Okay? So negative and negative, right? So equal to says I can use brackets. So I'm going to use all these values, and I get to negative 8. Should be a closed dot on negative 8, right? Now I come over here to negative 2.5, and we think should be a closed number or closed dot, but that negative 2.5 came from the denominator, right? So you got to make sure we keep it open. Okay, that's why I always put that there first. Because as you go through all this, if you don't put that there first, you go through all this work, you're going to forget that that factor came from the bottom. And you're going to accidentally close it. Make sure that you leave that open. And then we're going to graph to the right. And then writing that stuff in interval notation that is going to look like negative infinity up to negative 8, bracket, union, parenthesis, negative 5 halves to infinity, parenthesis. And that's how you graph these polynomial inequalities. That's how you write your solutions for these polynomial inequalities. And if we think about this, guys, we did a lot of like preliminary algebra 1, algebra 2 work here before we could do anything, right? Okay. I want to give you the picture of what this thing looks like in respect to this. Okay. If I look at x minus 3, divided by 2x plus 5, okay? And then I look at 1. Now I gotta have y equals 1. Get rid of that. Y equals 1, okay? We are asking the question, when is the blue curve, because we're less than, right? This is x minus 3 is less than 2x plus 5. So we're asking, when is the blue curve less than 1? Okay, so blue curve is less than 1 over here from negative 8 left, right? So negative 8 to negative infinity. So that was that interval there, correct? Okay. And then we come over here and we see that we are also at negative 2.5. You see you'd have a vertical asymptote there, right there, correct? Would you agree that the blue curve here from negative 2.5 to the right is always below that black line of y equals 1? Yeah, okay. However, it is much easier algebraically, instead of trying to figure those things out, because if I was trying to figure that out, I would have to find out where first, I'd have to set the equation of where these two things are equal. Okay? It's so much simpler to take the equation. What do we have? What do we do when we transformed it? We had negative x minus 8, negative x minus 8 over 2x plus 5. Okay. Now it's simpler algebraically to see where is that red curve, where is that below the x-axis instead of below 1. Does that kind of make sense, everybody? And it gets even simpler doing it that way when we look, and we're not going to have time to do this, but if I were to look at something like this, okay, there we have two rational functions, one on the left, one on the right. When I take the one on the left and combine it, it'll give me a rational function. It's going to be so much, or it's going to be very difficult to see where those two rational functions intersect and where one is below the other one, where one is above the other one. But if I can take all that stuff to the left-hand side, combine it to one ratio, and then look at where that one ratio is less than the x-axis, or less than 0, that's going to be so much simpler. Okay? There might be quite a bit of preliminary algebra in the long run, but it's simpler, less amount of algebra than if we would leave it this way and try to find the solutions that way. Okay? So, my hopes are that we have